So now let's talk about some topics which were left in electrostatics and electricity. So first of all, we will talk about dipole, electric dipole. The field due to the electric dipole. Electric field due to dipole and dipoles. So whenever there is a dipole, electric dipole given, let's say this is a electric dipole P. This is the center of this dipole. There is a negative charge here, minus Q, and a positive charge here, Q. And this is the direction of the dipole, from minus Q charge to the plus Q charge. And since this is a vector quantity, any vector quantity can be broken into components. For example, let's say in case of gravity, in case of solving questions in mechanics, we used to break the gravitational force acting on the body into two components, like this angle is theta, then this is broken into two components, g sin theta and g cos theta. So we used to break the vector into two components. Similarly, in case of dipole moment, this is a vector, so we can break it into two components. Let's say, and the two components are taken in perpendicular direction to each other. Let's say one component of dipole moment is taken in this direction, then the other component of the vector, dipole moment vector, would be either in this direction or in this direction, means perpendicular to this vector component. So the two components would be perpendicular to each other. So let's say this is a coordinate system x and this is y, and this dipole moment makes theta angle with this x-axis. Let's say this is x-axis line, this is a theta angle this dipole moment is making with this x-axis. So the component of this dipole moment I can take along this y-axis, I can call it py, and this is px. I can break it into two components, py and px, where px is equal to the component of this vector along this, which is p cos theta, and the component of this p vector along this is p 90 minus theta, cos of 90 minus theta, which is p sin theta. So I have taken the component of this dipole moment vector in these two directions, and I can now remove this dipole moment vector, and I will say that the sum of these two vectors will give py into j cap plus px into I cap. These two vectors will give the dipole moment vector which we had here at this point. The center of all these vectors are same. Let's say the dipole moment vector was this with center this C point. Then if I take one component of this p vector in this direction, let's call it p1, then the other component of this dipole moment vector would be perpendicular to this p1. Let's say this p2, this is perpendicular to it now, and the center of this p2 would be at this C point, and the center of this dipole moment would be at this point. So we can assume that if there was a minus q charge here and plus q charge here, I can replace it with a system where this whole system looks like this. one charge q1 here, plus q1 here, minus q here, and a minus q1 minus q2 here, and plus q2 here. I can write this p vector in terms of this, and it's my choice. A dipole moment's value is dependent on both length and the charge, the two charges, so the magnitude of the charge. So I can vary the length or charge for changing the magnitude of the dipole moment. Now one simple case of finding electric field using this dipole moment vector, breaking it into the components. So let's say there is a dipole moment here in the space P. This is the center point of the dipole. This dipole moment is pointing in this direction. Now if there is a point, let's say this point A, I want to find the electric field due to this dipole moment at this point, but I only know the electric field in the equatorial plane, that is perpendicular to this axis, and along this axis. I only know these two formulas. So how do I calculate the electric field at this point due to this dipole moment vector, which is making theta angle here? So in this case, what I can do is that I will take one component of this vector in this direction, let's call it P1, and another component of this vector perpendicular to P1 would become perpendicular to P1, which is P2. Now this P1 will become P cos theta, and this P2 will become P sin theta. Now I can remove this P dipole moment vector, and there would be two dipole moments here. The electric field due to this dipole moment at this point would be simply due to the field along this axis, and in this case we will use the formula of electric field due to a dipole moment in the equatorial plane. So this P1 force applies some electric field E1 here, and this P2 dipole moment applies some electric field here, let's call it E2, in this direction, in the equatorial plane of this dipole moment. The value of this E1 is equal to the formula of let's say that this dipole moment is very small. Let's say this is the length of this, let's say this is the half length of this dipole moment A, then A is very small than this R length. If it is given, then in that case the formula of electric field at any point is given by simply, if it is along the line, then it is given by K 2kp upon R cube, and in case of this equatorial plane, this E2 vector would be equal to minus kp vector, this is kp1 vector and this is kp2 vector, divided by R cube. These are the formulas of electric fields, and the net electric field at this point would be, let's say this E net, this would be the sum of these two electric field vectors. So now I can, using this concept of breaking the vector into two components, I can tell the electric field due to this dipole moment at any point which is at an angle theta, and this magnitude can be simply calculated as E net magnitude is equal to E1 square plus E2 square root, because E2 and E1 are perpendicular. This field is acting along this line, and due to this dipole moment, this electric field E2 is acting perpendicular to this line. Now the next topic is torque on a dipole moment and an electric field and the energy of the dipole. So first of all, whenever we have a dipole moment, let's say whenever we have an electric dipole, there is a minus q charge here, and there will be some length separating them, and there would be positive charge here. So there is a length L between them, and these are the charges. Then this system has some potential energy. This potential energy U is given by minus k q square divided by this length value only. So this becomes the potential energy of this system. And as long as the dipole moment's magnitude, as long as this length and this charge is fixed, means q and l are both fixed, then this u value is also fixed. And if the charge decreases and l increases, then then the value of this potential energy will also change. Means if these two values q and l change, then this value will also change. Just do the calculation to know how much it is changed. Now next thing is let's say there is an electric field, uniform electric field. There is a uniform electric field. Uniform electric fields means the field lines are parallel and the strength of the electric field is same everywhere, that is E. Everywhere the electric field is E, and there is a dipole, electric dipole placed in this medium here. Let's say this is dipole with its center here, see, and the length from this to this end is, let's say, half of the length of the dipole is A, and this dipole is making theta angle with this electric field direction. So with the positive direction of electric field, this dipole moment is making this theta angle. So this is the dipole moment vector and this is the electric field vector making theta angle between them. This is the smaller angle between them, and in this case we have, let's say, there is a charge q here, plus q, and there is a minus q charge here. This is the center, this is the length A here, similarly length A here. Now there is a force in this direction of electric field acting F on this plus q, which is equal to E into q, and on this minus q there is a force acting F on minus q, which is equal to minus of E into q. So these two forces are equal and opposite in direction, so the F net on dipole is equal to 0. The net force acting on the dipole is 0 in this case of uniform electric field, and this means that the center of mass of the dipole will have 0 acceleration. ACM will be equal to 0. That's what it means. And since if the center of mass is at the center at this point, then it will rotate about this point only in the medium, and it will be remain, if it is at rest initially, then this dipole, if placed in this electric field, this won't move anywhere in this space, only it can rotate in the electric field. And now talking about the torque, since there is a force acting in this direction F, this is the length from torque about this point, this center point, let's say this is the center point, then the torque taken about this center point can be written as this R cross F. This R cross F gives torque in this downward direction, and the value would be equal to EQ into A, and the angle between this R vector and this force vector is theta, so we will get EQA into sine theta. This is R F sine theta, force into this length into sine theta, and the direction is inward. Let's say this is inward in direction. And similarly, there is one more torque acting on this point. This is also in this clockwise manner, so this is also inward, and the magnitude is again same, EQA. The angle between them is same as theta, so this is sine theta. inward, and we find out that the direction of this torque about the C point, this is equal to P cross E. The unit vector of P cross E, the unit vector as P cross E gives the same direction as this torque. Means this dipole moment vector is in this direction and the electric field is in this direction, so the torque is in the downward direction. So the direction of this torque can be given by this, and the magnitude of this torque, this is the sum of these two, which is 2aq into E sin theta. So this gives P E sin theta. So the magnitude of the torque is P E sin theta. This is inward, and the direction is also given by the cross. So these two things, the magnitude and the direction, these two things tell us that torque can be written as P cross E. So this is our one formula here, that torque on a dipole moment, let's say P, is due to the electric field E, the torque on the dipole moment is equal to P cross E. This is the torque due to electric field E. And now we have derived the equation of torque, and now talking about the work done by the electric field. Whenever there is a torque acting or a force acting and the body displaces or rotates, there could be any work done. The force does work by doing some displacement. The work done can be written as dW is equal to F dot DSPA and this can also be written as torque about the IA over dot T theta, and this will give the work. This work can also be written like this, and it can also be written like, okay, let's leave it. Simply just know that the work done in the case of rotation, when the dipole moment rotates in this electric field, there is some work done by the torque, which is given by tau dot d theta. This is dW work done by the electric field. This is the work done by electric field. This is the torque applied by electric field. So the work done by electric field is equal to the torque applied by the electric field and the small rotation. Now we know one more thing, that this electric field, it is a conservative force system. So the work done by the electric field is simply equal to the negative of change in potential energy in that electric field. So knowing this relation, I can say that minus due is equal to tau due to the electric field dot d theta. This is vector. Now integrating this from, let's say I am rotating it from a smaller angle θ1 to a larger angle θ2, means in this electric field the dipole moment I am rotating it from θ1 angle to some larger angle θ2. Then in that case the potential energy changes from initial potential energy to final potential energy, and this torque can be written as P cross E dot d theta vector taken from θ1 to θ2. Now in this case, if we see that the electric field is in this direction, the dipole moment is in this direction, and if I rotate this dipole moment in this anti-clockwise manner while the torque acting is in the clockwise manner, so the product of this torque and this angular displacement, this will be a negative value. So I can write it as integration from θ1 to θ2 minus P E sin theta d theta. Solving this vector products, we will get a minus sign here, and the magnitude will be written like this. This is a dot product. Now integration of this gives minus PE, and the integration of sin theta gives minus again, so we get a plus sign here. Minus into minus will give plus, and bracket में cos theta 2 minus cos theta 1, that is equal to the u final minus u initial minus sign here outside. So this is the equation of the work done in this case of rotation in the electric field, uniform electric field. Now in a convention is taken for potential energy. A reference potential energy is always taken to simplify the questions, because to make it so that we can write the potential energy at any position, so that we can define the potential energy at any position, I will take a reference so that u initial is when u initial, I am taking this u initial as the reference state, and this reference state is the case when P and E makes 90-degree angle. So the initial case, the initial state, the reference state is the state when this electric field and this dipole moment vector make 90-degree angle with each other. This is our reference state. This is the reference state, and in this reference state the u initial value is taken as 0. So the u when the angle between these two is 90-degree, that is equal to 0. So u initial I have taken at 90-degree, and at 90-degree I have taken the potential energy as 0. So I can write this as 0 here, and since this initial angle is 90-degree, this will become 0. This gets eliminated. Now since there is only one theta here, I can simply write this theta 2 as theta for simplicity. So this will give the formula of minus u at any angle theta is equal to PE cos theta. At any angle theta, the potential energy is equal to PE cos theta minus, which is simply u at any angle theta is equal to P dot E minus P dot E. So the potential energy can be written like this: u at any angle theta is equal to minus P dot E. Here for this case I have taken this assumption. This assumption is important to note. Only then we can derive this relation. So it is important to note that potential energy at 90 degrees is taken 0 joule. Now this topic is over. Next topic is about capacitors. Or am I forgetting any other topic? I am not. Yes. So the next topic is, let's move to the next topic, capacitors. In case of capacitors, let's say there are two capacitors. One is C1, one has C1 capacitance, and one has, let's say, C2 capacitance. This is initially charged with, let's say, here it is positive charge, negative charge, here it is positive charge, and here it is negatively charged. These capacitors are initially charged. It has, let's say, Q2 charge initially, V1, V2 potential difference across it, and this is, let's say, Q1 charge and V1 potential difference across it. And we know that C2 is equal to Q2 by V2, C1 is equal to Q1 by V1. That is the basic definition of capacitance. Now if I take these two capacitors and join them in parallel, there are two ways to join them. Case one is, if I join this positive end with this positive end and this negative end with this negative end, means this is positive side of this capacitor, this is negative of this C1, and this is C2. This is again positive side and this is negative side. I have connected the positive with positive, negative with negative. There is case 2. The case 2 is when this positive side of capacitor 1 is connected with negative side of capacitor 2. Now what happens if there is in this case of case 1 there is some potential difference across it, V1 and V2 across it. If V1 is unequal to V2, there would start a charge flowing from one capacitor to the another capacitor, and this current will flow as long as until the potential on this plate V1 dash becomes equal to V2 dash, and let's call these final potentials as, or I can write it as V1 final and V2 final. They become V0. So the final potential difference across these two capacitors becomes V0. Across this or across this, these two becomes V0. After the potential difference across both becomes same, then in that case the charge flow will stop and this will become at equilibrium state. This system will become stable after they both gain same potential difference. And the direction of the potential difference is also important to note, that positive air, negative air, negative air. So it means that if I go from this side to this side, if I take the, let's say this system has some resistance, little bit very small resistance R, which is very small resistance, let's say, and when I take the potential difference, let's say at any instant the potential difference across this capacitor is, let's say, V1 dash. So if I take the potential difference in this loop, in this anti-clockwise manner, I will get V1 dash. Then let's say there is some current I flowing in this circuit, which is minus I into R, and then this potential difference I will take it as minus lesser potential minus higher potential, which is V2 dash, that is equal to 0. So as long as unless these two potentials become equal, when these two potentials become equal, this minus IR will become 0. This means current will become 0. So when these two potential differences across them becomes equal, the current will stop flowing in the circuit. That's the simple logic. Now we know that in case of, since there is, let's say, Q2 charge in this plate and Q1 charge in this place initially, and after some time when this equilibrium is reached, there is Q1 charged on this plate and Q2 charge, this is Q1 and this is Q2. Let's say it becomes Q1 and Q2 in final case. Since the total charge on this plate is conserved because charge cannot be destroyed, so Q1 plus Q2 should be equal to Q1 plus Q2, and we know that Q1 plus Q2 can be written as C1 V0 plus C2 V0. This is the final charge, and Q1 can be written as C1 V1 plus this Q2 can be written as C2 V2. This gives V0 is equal to C1 V1 plus C2 V2 upon C1 plus C2. So that is the formula of potential at equilibrium state. This is at the equilibrium state. And when these two capacitors are connected in opposite manner, let's say negative side is connected to the positive side, then in that case, let's say it has minus Q charge, minus Q1 charge initially, this is plus Q1, this is minus Q2, this is plus Q2. Now what happens is that, let's say some current flows from in the final case there is need of in the end, in the final case, we need same potential, same type of charge on these sides. In the final stable equilibrium, there will always be same type of charge on the same sides. It is not possible that there is opposite sides, opposite type of charge, and in that case, and why it can't happen, because let's say I take the potential across the loop in this anti-clockwise manner, then this would be, let's say that the potential difference at any instant across this capacitor is V1 dash, and if it is negative here and positive here, then the potential difference across this would be given as plus V2 dash, and the current here would be, let's say, I, and there would be some resistance, then it would be given as minus I. Since current flows from positive to negative side, it would be given as minus IR, that is equal to 0. Now, since if there is negative charge here, if we assume that in the final state there could be any positive negative charge here, then since these two are positive values, this value will never become 0, will never be equal to 0. So this means this current will never be equal to 0. So we are assuming that a stable equilibrium is reached and there is some negative charge here, positive here, means this type of arrangement in final case, but it contradicts that current is not 0, means it is not stable. We assumed that it is stable, but it is not stable. So it says that to get a stable equilibrium, when you connect two parallel capacitors, they must have same type of charge on the same sides. So this negative, there would be some negative charge here and positive charge here. On the same side will be positive charge. Only then the current will become, only then the current can become 0, because now this sign will become negative here, and now this can become 0, and when this becomes 0, this can become 0 also. This was one important point about capacitors. And now when let's say initially this side has Q1 charge, this side has minus Q2 charge, and finally this will get some Q1 charge, and this side will get some, let's say, Q2 charged. They both will have same type of sign. So if it is negative, if Q1 is negative, then Q2 will also be negative. If Q2 is positive or Q1 is positive, then they both will be positive. So one thing I can say here is that Q1 dot Q2 is equal to, is greater than 0. The sign must be same for both. And now I can say that Q1 minus Q2 can be written as C1 V1 minus C2 V2, which is either equal to this value which is given as V naught bracket C1 plus C2, or it can be equal to our minus V naught bracket C1 plus C2, because the charge can be negative or the charge can be positive. Means if Q2 becomes large, then this value becomes negative, and then in that case we have to take this sign, and if this Q1 is greater than Q2, then we'll have to take this sign, because positive values will be equated to the positive. So I can simply say that V naught C1 plus C2 is simply equal to the, since this is a positive value, I can say that it is equal to C1 V1 minus C2 V2 modulus. So this gives V naught is equal to C1 V1 minus C2 V2 modulus divided by C1 plus C2. This gives the magnitude of the potential difference across the capacitor, And if I want to know the direction of the potential difference, then I have to assume one sign. And how will I assume the sign? Let's say, and to know the direction of this potential difference in the final case, we can simply use our logic that let's say this q1 is greater than this q2, then the net charge on this side would be positive. So the side which has total positive charge, this will get positive potential in the end, and this side would get negative potential, and that would tell the direction of the potential difference. V naught would be from, this would be potential difference across this, where this is higher and this is lower potential. Now if I say that this q1 is lesser than q2, then since this is a negative, the value, then in that case this side will have a net negative charge even after equilibrium state. So we will say that there would be some negative charge here and negative here, and in this on the opposite side there would be some positive charge. So the potential difference in this case would be like potential is higher at this side and lower at this side. So this is how we can judge the direction of potential difference. So this, in case of this same side shaded, same charged plate added on the same side, then we get this formula of this addition, and when we have opposite charged plate sides added together, then we get this negative sign here. This is a negative sign we use here. And let's say I remove this modulus sign from here. Now it means that if this value is negative, if this value is positive, then it would mean that the side of the capacitor 1, this is the capacitor 1, then the sign of the potential would be same as the V1. Means if this value is larger, then this Q1 will dominate over this Q2, and the potential difference direction would be same. This would be high and this would be low. This V0 will be same as the V1. Means these two will have the same signs across this capacitor. And if this becomes less and this becomes large, means this value becomes negative, then this value, this V1 potential difference will have opposite sign with V0. Means if V1 potential has higher potential here and lower here, then V0 will have higher here and lower here. That's what it would mean. So we can understand through this way. Just remove the modulus and understand from the sign of this value. So we take positive in this case of same side, and opposite sides when added, then we take negative. Previous case, the formula we have derived, this can also be understood by a simple concept that of equivalent cases, like let's say this whole system gives a single capacitor here, and the charge should be conserved. This side will get Q1 plus Q2 charge, this side will get minus of this Q1 plus Q2 charge, and we know that the net potential difference across it, let's say it is V0, then, and if the total capacitance of this capacitor is, let's say C0, then we get C0 is equal to the total sum of the charge Q1 plus Q2 divided by the V0. And we know that in case of parallel combination, the capacitance is simply C1 plus C2. So the C0 is equal to the C0 combination of this capacitor is C1 plus C2. This gives this formula. Simply I can write this V0 as Q1 plus Q2 divided by C1 plus C2, where Q1 is equal to C1 V1, Q2 is equal to C2 V2 divided by C1 plus C2. So that formula can easily be derived by this concept of parallel combination of capacitor and conservation of charge. Similarly, in this case, let's say opposite sides are added, then we will get, let's say this is Q1 charge here and minus Q2 charge here. Then I know that the capacitance equivalent is equal to C1 plus C2, that is equal to the total magnitude of the charge, which is, let's say, Q1 minus Q2. The total sum of charge is this. The magnitude of the charge is given like this. We don't know if this is larger than this, that's why we will take a modulus here, because the charge value put here is positive and divided by the potential difference V0 at the equilibrium state. This gives V0 is equal to C1 V1 minus C2 V2 modulus divided by C1 plus C2. So this is how we can easily derive this formula, just using this concept of equivalent capacitance and conservation of charge. Now this gives equivalent case of capacitor with capacitance C1 plus C2, and the total charge here is Q1 minus Q2 magnitude. The magnitude of the charge on this capacitor is Q1 minus Q2 magnitude, and we don't know what is the sign of this charge. It can be negative or positive. Let's say this is Q1 and this is Q2, then charge at this side would be Q1 minus Q2. Now moving ahead, the next concept is of heat loss. Whenever there is a capacitor, we know that there is some energy stored in a capacitor. Let's say this capacitor C1 initially stores some energy given by V1 Q1 by 2, that is the energy stored in the capacitor 1 initially, and finally the capacitor 1 will store energy is equal to V0 Q0. Let's say Q0 is the final charge on the plate, not on the plate. Let's say they get added and they give, this plate will have this E2 plate will have initially V2 Q2 energy, and when they get combined parallelly they give an energy equal to V0 bracket, the total charge is conserved, which is Q1 plus Q2. This will be the final energy of the system is this, and the initial energy of the system is equal to the sum of these values, and this value is smaller than the sum of these two values, and the difference of this E final minus E initial, the E initial is greater than E final, there is always some loss, and E initial minus E final is equal to some heat energy lost, that is equal to the heat energy lost, which is equal to, it is given by the formula 1 by 2 C1 C2 divided by C1 plus C2 bracket V1 minus V2. We can derive this formula by subtracting this E final from this E1 initial. So this is the formula of heat loss, and this is for the case 1. This is for the case 1. Here we have minus sign here, and in case of this heat energy is given by similarly the same formula here, C1 C2 divided by C1 plus C2, but here we have V1 plus V2 whole square. So the heat loss in this case is given by the sign in this case. In the case of V0, we saw that the sign here was C1V1 plus, in this case was C1V1 plus C2V2 divided by C1 plus C1. There was a positive sign in this case of same sides in case of V0, but in case of heat energy there is a negative sign used here, and in case of this the formula of V0 had a negative side here, it had a negative sign here in this case, and in this case this will have a positive sign here. So this is what happens. Now this concept is over. Now next topic is charging a capacitor using a battery or a DC supply or a constant voltage supply. So let's say there is a capacitor with capacitance C, and there is a resistor here of resistance R, and there is a cell here, DC battery with some voltage V is connected to this capacitor. There is a switch here, let's say, and at time t is equal to 0 there is charge on this plate, Q is equal to 0, there is no charge on this plate, and I switch on it. Then what happens, this current will start flowing in this direction from this positive plate, and there would be some positive charge stored here, some negative charge will start storing here, and this process, and the charge will keep increasing on this capacitor, and this potential developed across this capacitor, let's call it VC, this will oppose this current, this will reduce the amount of current with time. With time this charge increases, the amount of charge increases as the current flows, and this VC also increases because the current produces some charge Q on this capacitor, and as Q increases VC increases, and VCS increases, this decreases the current, and it means slowly the system starts slowing down, the current starts reducing in the circuit. Now making the equation and calculating all the values. First of all, we know that first important thing is that Q is equal to, or we can say that we know that Q by VC is capacitance, the Q charge is stored at any instant, and VC is the potential difference across capacitor at any instant. Then we can write VC is equal to Q by C is equal to C, so Q is equal to VC is equal to Q by C. Now the second equation, we know that we apply KCL in this circuit. Let's take the loop in, let's consider the loop in this direction. So starting from this point, I take potential difference across this is positive side, this is negative side, so the higher potential minus lesser potential will be V, positive value. This V is always a positive value, and now let's say there is some I current flowing in this, then since the current is flowing in this direction, there would be a high potential in this at this side and less potential at this side. It means the potential difference, the magnitude of IR is positive, but the potential difference, this potential minus this potential is lesser, negative, so I will take a negative sign here. Simply we can say that if the current is in the direction of conventional positive direction of loop, then we will take a negative sign with it. Now in this case, this positive side will cause a positive charge to develop here, negative charge here, so this will have a higher potential, this will have a lower potential. It means low minus high will give a negative potential. VC is a positive value, so we will take a negative sign here, and this total value this potential is equal to the potential here, and finally we have reached the same potential. This will be equal to 0, the potential difference across the circuit. Now we can write V minus Vc is equal to IR, which gives this equation. This gives I is equal to Vc can be written as Q by C. This is divided by R, that is equal to V by R minus Q by CR. That's it. The current in this circuit is this, and this current, now using this first equation will give I is equal to dq. First equation is used here. Now I can be written as dq by dt, that is equal to V by R minus Q by CR. Now I can integrate using this equation, differential equations. This is the third equation. Let's say this gives dq over dt is written as V by R minus Q by CR. So let's multiply both sides by negative sign. This will get negative here, and a negative sign here, positive becomes here. So now I am dividing this by Q by CR plus minus V by R. I'm dividing by this, taking dt on the right side. Now integrating this whole from, let's say, initial state of 0 time to the time t, and this is integrated from 0 charge to any charge q at any time t. Then in that case we will get t here, and let's say this whole value q by CR minus V by R is equal to Z, then dz is equal to dq over CR. This gives this integration from z initial to z final minus dq is equal to dz and to CR divided by this z, that is equal to t. Now integration of this will give CR minus ln of z2 over z1 is equal to 2. Now this z2 over z1 can be, the final value of z2 can be written from this and initial value at the denominator. Now I can write it as the final value of z is, the charge stored finally is q, so it will become q by CR minus V by R, and charge initial is 0, so z is equal to 0 by CR, this will give minus V by R. So now I can write ln of, now dividing this part with this, V R gets cancelled in both, and now I divide it by V, I get minus 1 here, this V get cancelled and V gets here. Now taking this on this right side, I get minus CR here, and now taking the anti-log we get q by CV minus 1, this divided by minus 1 is equal to e to the power minus t over CR. Now multiplying this, taking this minus 1 sign here, this will give q by CV minus 1 is equal to minus e to the power minus t by CR. This gives q is equal to CV bracket 1 minus e to the power minus t by CR. That is the formula of charge stored. On the capacitor at any time t, where C is the capacitance and R is the resistance present in the circuit. Now for complicated circuits we can write this formula, and we have some tricks for complicated circuits for this value, for putting the value of resistance. But before that, let's derive the equation of VC and I in the circuit. VC is simply equal to, we know that VC is equal to QIC. So simply this Q, we will divide it by capacitance and we will get the value function of VC. VC is equal to V, C get cancelled, V bracket 1 minus e to the power minus T time divided by CR. So this becomes the equation of capacitance, potential difference across capacitor, and this I will be equal to dq over dt. This I is equal to dq over dt. It means this is constant value CV, and differentiation of this 1 is 0, and differentiation of this value will be minus e to the power minus t by CR. It will remain same. Now I will differentiate this whole value with dt multiplied by differentiation of this will give minus 1 by CR. That gives V by R bracket minus minus becomes plus. This would be minus t by CR, e to the power minus t by CR. C to C cancels and V by R we get here. So the current formula will become this. Potential difference across capacitor would be this, and this is the charge on the capacitor. These are the relations with respect to time. Now these are the formula for charge, current and potential difference. Now if a circuit is complicated, let's say, well, this CR here is, this CR can also be written, CR is written as tau, which is equal to, what is this called, just 1 second. This tau is called, this product of C and R, capacitance and resistance in the circuit, is called time constant. This is called time constant. So I can write, instead of CR I can write a tau here, and tau here. Now the value of tau, we can find this by simply, this tau is more properly written as C into R net. The more proper equation for this tau is C into R net, and this is the R net. This value here is the R net, and let's say to understand this R net value, let's see some circuit. Let's say there is a capacitor here, there is a resistor here, and there is a cell here, there is one more resistor added here parallel to this capacitor. This is R1 resistance, this is R2 resistance. Then R net means, let's say this point is A and this point is B. Then R net in this case means R net is equal to R A B. Let's say this cell is replaced, this cell is of some internal resistance R, so I replace this cell by a resistor R here of this its internal resistance. Then in this circuit, the equivalent resistance RAB would be equal to the R net. That is the resistance across this capacitance, that is the R net. So in this case we see that this is the point B and this is the point A, and this is R1 R, and this another part of this another resistor is R1, and this is also connected in parallel to this circuit which is R2. So these two resistors are added in parallel. So RAB, in case of parallel, RAB is equal to 1 upon R1 plus R plus 1 upon R2. So RAB is written as this, and this R net is equal to this RAB. That is the resistance across this AB. And this R net will give this tau. Tau is equal to C times this R net value. R net. That's it. And if we are given two capacitors here in this series or let's say parallel, then we will take the combination of the capacitors. So this was it. The topic is over now. What topic is left now? I guess one more few formulas we should remember. One is the case of, I guess, not given here. Few cases of resistors added. Okay, let's solve some resistance calculation. Equivalent resistance calculation. So equivalent resistance can be calculated by using simply KCL rule. KCL rule is the best. This is the best rule. This can help in calculating the resistance in any complicated system. For example, there is a cube here. This is a cube here. This is a cube here, and each of these sides, each of these lines I have drawn, these are of resistance. Let's say R. All are of resistance R. This is R, and R. All are of resistance R. Now I can ask what is the, let's say this point is A and this point is B. These are the diagonals on the same face. This is the shortest diagonal. So for the shortest diagonal, the resistance is the equivalent resistance we have can be calculated by applying Kirchhoff's circuit rule. Then that is simply, let's assume there is a cell applied. Then let's assume there is a cell connected to this A and B. This is of potential V. Let's assume there is a cell of potential V, potential difference V, and some current flows I through it, and it gets divided in I1, I2, and then it gets divided further. And since this is symmetrical, these two shapes are here this case is very symmetrical. We can easily tell that this I1 would be equal to this I2. These two would be equal because this shape is very symmetrical. This will go in this direction divided, and after that some current will go in this direction. Sorry. Okay. If I'm right, these two are symmetrical, and there would be some current in this direction I2. Some I1 current flows in this direction, I1 in this direction, and some I2 in this direction. And the sum of this 2 I1 plus this I2 would be equal to I, and Then this I1 current divides into two parts. Let's say this is I3, then this will become I1 minus I3. Similarly, this happens in this case. This current is I3 and this is I1 minus I3. Now we can apply KCL first across this loop, and then across this loop, and one more across this loop. So by making these loops, I can get equations in the variables I1, I2, I3 ... and I. And after I get equations in these variables, I will have to write the equation in some form of, let's say, V is equal to I into some constant value K. That would be given by the sum of some resistances. And let's say if my equation turns out I have to use all this equation and make equation in this form, somehow in this form, then this constant value, which is the coefficient of current here, this I is the current passing through this battery, then this constant would be called as RAB. RAB is equal to K. This would be called as the effective resistance. So this is how we calculate. We have to make this form of equation, and the coefficient here K will become, this will be called as equivalent resistance.